This is the second video on Markov chains. And in the first video, I showed you how to define the transition frequency matrix of for a section of four lithologies, and then to convert that transition frequency matrix to a transition probability matrix. Now, the last step that we had was to test whether there's any dependencies between the lithologic units or if the section is just made up by the sequence completely randomly. So to do that, first, what we're going, so what we're, so perhaps to summarize what we're going to do, so the overall strategy is to compare our observed transition frequency matrix with the transition frequency matrix big T sub 0 for completely independent lithologies. So we can predict what the transition frequency matrix should be if all the lithologies are completely independent of each other. And we'll compare that using our chi-squared goodness of fit test. So that's the overall strategy. And the steps are, first we have to compute P0, the transition probability matrix for independent lithologies. Then we convert P0 to T0, and then finally we do our chi-squared test. Okay, let's start with how to compute P0. So if you recall back to our rules of joint probability, we learned that the probability of A given B is simply equal to the probability of A if A and B are independent of each other. And Wessel goes through a derivation of that, but if A and B are completely independent of each other, existence of A shouldn't depend on whether B is present or not. It's just the probability of A. Or we could write the component, so recall that little p sub ij is the probability of lithology J given lithology I, and that simply becomes the probability of J. So if this is the case, that is, if state I is independent of J, then the probability transition, the ijth component of the probability transition matrix for independent states is simply equal to P, the probability of each lithology. Right, we're solving for P sub 0, the case in which all the lithologies are independent, and we have to find each component of it, little p0 sub ij. So let's look at our row total vector. So Ri was the ith component of our row total vector, and that was the number of transitions from lithology I. And if that's the total number of transitions from lithology I, it's also equal to the number of occurrences of I. Actually, let me let me change this I to j just to be consistent. So the jth component of our row total vector describes the number of transitions from lithology j, and it's also equal to the number of occurrences of lithology j. And so the probability, the marginal probability of j, that is the probability of j anywhere, independent of any of what occurred prior to it, is simply equal to the number of occurrences of j divided by the number of all transitions. So that gives the probability of j given I for independent lithologies, and that's our ijth component of our big P0 matrix. So Paul Wessel puts this into a vector. F is equal to the marginal probability. It has each component is the marginal probability of j, and that vector is the marginal probability vector. It's the probability of each lithology, irregardless of what followed it or what preceded it. So in our example, if we take our row total vector and divide by the total number of transitions, we get a marginal probability vector of 30% of the 36% of the transitions occurring, or 36% of all points being lithology A, 12% being lithology B, 44% of all points measured being lithology C, and 8% being D. And so the transition probability matrix for independent lithologies has all the rows made up of that vector. So little p0ij is equal to f of j. So each component of f makes up each column of little p0. So now that we've defined p0, we have to convert p0 to p0, the corresponding transition frequency matrix. Okay, so you recall that when we had our original transition frequency matrix, we converted it to a transition probability matrix by dividing by the row totals. Here we have a transition probability matrix. To convert it to a transition probability matrix, we have to multiply it by the row total. So with the transition probability matrix having components little t sub 0 ij, then each component is equal to the transition probability, the ijth component of the transition probability matrix for independent lithologies times the row total. So each column of P0 is multiplied by the vector of the row total vector. And let's see, so in MATLAB, for example, we would write T0 is equal to diag with the components of R on the diagonal of this 4 by 4 diagonal matrix times, and this is a vector multiplication, P0. And the solution we get when we do that is right here. So finally, we can do our test. And our test, let's say our null hypothesis is that the sequence, the parent sequence sampled is made of made of lithologies that are independent of each other. And the alternative hypothesis is that some lithologies depend on some lithologies. Or some lithologies depend on the preceding lithology, and in our case, the preceding lithology is what is occurring 1 foot below it. So as I mentioned, the strategy is to compare T, our observed transition frequency matrix, with the transition frequency matrix for independent lithologies, and we're going to use the chi-squared goodness of fit test. And if you recall, chi-squared was equal to the sum over k different bins of oj minus ej squared over ej, where oj equals the number of transitions in bin j and that'll be based on t, the observed transitions, where ej is the expected number of transitions in that bin. And that the expected number will come from the components of T0. So recall that we need, so each bin must have greater than 5 elements, or in this case, transitions. So what we're going to do is break up our T and T0 matrix into a number of bins with greater than 5 transitions that represent greater than 5 transitions. So I've obviously written out the two relevant matrices. And so we can see that the first element of T has greater than 5 transitions. So I'll make that bin 1. The transition from A to C has also 5, so that'll be bin 2. The transition from C to A has 5 occurrences, so I'll make that bin 3. And the transition from C to C has 17 transitions, so that'll be bin 4. Bin 5, let's see, let's make bin 5 everything involving a transition from B. So this whole row will be bin 5. Let's make bin 6 the whole row involving transitions from D. And then what do we have left? We have the transition from A to B, transition from A to D, the transition from C to B, and C to D, and we'll put that all in one bin 7. Okay. So we'll mark the corresponding bins in T0. So let me move that. Let's go to the next. Let me give myself a little more room here. So chi-squared becomes the sum of the number of bins, the observed number of bins in bin 1, which is 17, minus the expected, which is 17.9 squared all over, 7.9 all over 7.9, plus the observed number in bin 2, which is 5, minus the predicted, which is 9.7 squared over 9.7. For the third bin, we have 5 minus 9.7. The fourth bin, we have 17 minus 11.9. In bin 5, we have the sum of the second row of T, which is 7, minus the sum of the second row of T0, which is also 7. For the sixth bin, we have the sum of the bottom row of T, which is 5, and the bottom row of T0, which happens also to be 5. And then we have one more term, which is the sum of the checked values in each matrix. And that gives a value of chi-squared of 19.57. So now let's define our number of degrees of freedom. And recall that our matrices are m by m. But also recall that the rows of the transition probability matrix have to sum to 1. So we lose 1 degree of freedom. So the number of degrees of freedom is not m by m, it's m minus 1 squared. And let's define our our significance as, in this case, 5%. And so the critical value of chi-squared is chi-squared of alpha, which is 5%, and our degrees of freedom is 3 squared, which is 9, and that turns out to be 16.9. And just to remember, in MATLAB, you do chi2 inverse, and we're looking at the right tail here, and so we have to put in 0.95 and 9 in MATLAB. In the table, you would look up alpha, which is equal to 5%. And we find that chi-squared, our observed value of chi-squared, is greater than 16.9. So we must reject our null hypothesis that all the lithologies are independent. And the result is that there is some evidence for a dependence of successive lithologies at the 5% significance level. So this concludes example 5-1, and this was a first order Markov chain. As you recall, we could have higher order Markov chains or a dependence of states multiple steps separated. So again, P was the transition probability between one step, or in the example given of our lithologic section, that was 1 foot apart. So the transition probability between single steps or single feet. And this is our first order Markov chain. If we take P and multiply it, do a matrix multiplication by itself, that gives us P squared, and that's the transition probability for 2 steps. And this would describe a second order Markov process. And to write that out, this is equal to the sum from k equals 1 to m of little p I k little p k j. So let's see, the ijth component of the second order transition probability matrix is, again, the matrix product of the first order probability transition probability matrix. Or in other words, it's the probability of transition from I to j through all possible other states. right? So it's the probability, so little p ij is equal to the probability of going from I to state 1 to state j plus the probability of going from I to state 2 to state j and so on. So this gives you a little bit of intuition for, well, a different way of showing why the second order Markov process is described by the product of P with itself. And as I mentioned before, the kth order transition probability matrix is P multiplied by itself k times. And just as we did for our first order Markov chain, we can also test whether there is a dependence after k steps. So the transition frequency matrix after k steps is again equal to the diagonal matrix with our row totals times the transition probability matrix after k steps, and we can compare that using chi-squares to the transition probability matrix after k steps, assuming the lithologies are independent of each other. And it turns out that, well, since they're independent of each other, it doesn't matter how many steps there are between that you're considering. So T0 raised to the kth power multiplied by itself k times is equal to T0 itself. Okay, well, I think that should conclude my discussion of Markov chains and testing for dependence of successive states. And we've shown how to apply that to our lithologic section. And you can imagine there can be lots of other applications as well.